useful this way. And I'm going to give you an example of how calcium can stick onto a protein and then change two shapes. So a signal is then relayed by the secondary signal transduction pathway, and it's increased by the presence of calcium in the cytosol. So calcium signal to the cell. How's that? Now, on first glance, I don't know about you, sometimes and it's a matter of time. So if you really want to know something, you can totally get into it or not. And so check this out. Let's say that this is a muscle cell. Okay, let's go there. Say it's a skeletal muscle and we want it to contract. That's the response. So how do we get a muscle cell to contract? Well, the signaling molecule might be a message from the axon terminal of a neuron, a motor neuron in particular. Maybe the secondary message, the first message is acetylcholine. Maybe it is. So if this attaches here to a G protein coupled receptor, that's going to activate the G protein, which is then going to activate another enzyme, which is going to initiate another reaction, which will produce this inositol triphosphate. And this secondary message is going to come along like this, and it's going to come like this. This is a triphosphate. And check out what it does. It attaches to a protein on the endoplasmic reticulum membrane. Now, this particular ion gate is active, meaning that it can open and it can close. And so normally it's closed. And so it can become activated or open when IP3 attaches to it. And when it attaches to it, it's referred to as a ligand-gated active calcium ion channel. So long story, calcium comes pouring out. It's like sort of like you're opening up the floodgates, and they're coming out, and the calcium's coming out. And you're like, well, what's it going to do? What's calcium going to do? And you're like, well, the secondary message is going to cause a cell response. You're like, well, give me an example of how calcium can cause a cell response. I will. So here's a typical muscle cell here. Now, when I say a muscle cell, I don't want to get into the detail of this, but there's many muscle cells. When you think of muscle, this is the tendon connecting a muscle to the bone here. Now, these little bundles right here are called fascicles, and when you remove them like this, each one of these is a muscle cell. Muscle cell kind of works. It's really long, and it's tapered, and the inside of it has so much protein, so many microfibrils, that it almost doesn't even look like a cell. This yellow region right here is the endoplasmic reticulum of a muscle cell, and that's where calcium is stored. We call it sarcoplasmic reticulum when we talk about muscle. But sarco means flesh, and everything's sarcoplasmic. And the whole thing, it refers to sarcolemma is the membrane, and sarcomere is the sort of unit of the muscle cell that shortens. So I'm making a long story short on this, believe it or not. But how a muscle cell divides is that you have thick protein filaments called myosin, and thin filaments called actin, and those two slide past each other, and the whole muscle cell shortens. And you're like, well, how's that? Well, the myosin grabs the actin and pulls it in. And so therefore the whole thing shortens. Now, if you're following this, you're like, well, I only want a muscle to contract when I tell it to contract. And so herein lies the control. And so it will contract. It will contract when calcium is present. Now, I don't want to divert you for excuse myself in explaining this, but there's another video I produced on muscle contraction. I can sort of kindly suggest that you watch that video, because I'm not going to go into the detail of this, but it's really cool to touch on it briefly. What prevents myosin from interacting with actin is that there's some regulatory proteins. This long thread is called tropomyosin, and this little purple guy is called troponin. What happens is the muscle can't contract if tropomyosin is blocking the active site of actin right there. It won't contract. So what calcium does is that calcium, let me draw this out. What calcium does, let me go green because calcium is shown here in green. What calcium is going to do is interact with a protein called troponin, and it's going to change the shape of troponin, which then changes the shape of tropomyosin, which then opens the active site of actin, and then myosin is going to grab it and pull it in, and a muscle is going to contract. That's the cell response. So calcium acts as a secondary cell response messenger. And so check this out. This is sort of an illustration of what's happening here. Here's the tropomyosin, and that yellow is the protein troponin. So both those things are regulatory. And so calcium, shown in red, attaches to it, changes its shape, and therefore the muscle is able to contract. So that concludes our discussion on signal transduction pathways. I hope you enjoyed it. I hope you learned a lot from that. Thanks for watching. Hi, everyone. Mr. Cinti, and I'd like to talk to you today about primary growth. And primary growth is going to be a conversation that we're going to have that's going to sort of circle around the idea of apical meristems, which are, if you recall from a previous discussion, those sort of well springs of cells that are capable of mitotic division even as the plant gets older and older and older. So primary growth is going to be about the plant growing ground, vascular, and dermal, and it's sort of going to wrap